Hello. I decided I was going to try a little project to see if I could calculate the Earth's radius. I've seen several people do that before as well, but unfortunately, I'm a little bit landlocked where I am, and I have a few challenges, like the fact that where I am, there are not that many hills, or at least not hills of any significance. The main way that the Earth's radius was computed was done by Alberuni. Eratosthenes did calculate the Earth's radius before. The Alberuni method involves measuring this angle, knowing that this angle is 90 degrees, and with a little bit of trigonometry, you can find the radius of the Earth. So unfortunately, where I am and the current situation that we find ourselves in, I can't cross the border to go to one of the lookouts of the Gatineau Hills and look back towards this point over here, for example. So I decided I was going to try to approach this from the other direction. If I go to the Nepean Sailing Club over here and I go and stand right around here somewhere and I look off in this direction, I should be able to measure an angle up. I've got a theodolite app on my phone, so I was able to get some kind of reading. This is my last outing, and I'm going to be talking about this in just a minute, but not to mention that the phone doesn't have much to work with, and I had huge errors introduced just in the measurements alone. After the first outing that turned out to be a bit of a failure, I decided I was going to try approaching the problem from a slightly different angle. I found this website, www.calculator.net. If you provide 3 values, it will calculate the other 3 values. So I decided I was going to approach the problem knowing that the Earth was round and that the Earth's radius was already known. So I used Google Earth to get the terrain profile of a direction. I found several peaks and what the height should have been. So, for example, this height here would have been somewhere around 350 meters, and it would have been 16.4 kilometers away, for example. So I would have said the angle is 16.4 kilometers away. The height would have been 347 meters, for example, above mean sea level. And my observation would have been, let's say, maybe 55 meters above mean sea level. So given the length of all 3 sides, I said calculate the angles. And so it would have said if I was at the Nepean Sailing Club looking off at that point, I should expect to see an elevation angle of 0.946 degrees. If I happen to be at that point looking back over here, I should expect to see an angle below my horizontal of 0.906 degrees. So I could do that easily enough if I could go to each of those locations with a professional surveyor's theodolite and to be able to measure the angle that way. Unfortunately, I don't even have any reasonably accurate way of measuring it, and I'll get to that in just a minute. So I decided to work around that problem by finding a reasonable way of estimating this angle if I know this angle and this distance. So I've created a number of sample scenarios. The cells that are in yellow are those that I should expect to know or to be able to accurately measure. So in this case, if I'm standing at an elevation of 55 meters and I'm looking at the top of a hill that is 206 meters above mean sea level. All of these are above mean sea level, and I can accurately measure the distance between the 2 points. With a reasonably accurate theodolite, I can measure this angle. The idea is to be able to calculate this angle back to my location. So I use this triangle calculator with the knowns Earth radius of 6371 kilometers, and these would be the meters above mean sea level. This is the distance between the 2 points, and I got the far angle looking back at my angle. So the way that I estimated the zenith angle approximation from the hill back to my location, I looked at the problem this way. If I'm standing above mean sea level, I look down, the blue line would represent the angle to the sea. The red line represents my horizontal eye level, and the black line represents the angle up to the peak of a mountain or a hill that I'm looking at. If I happen to be standing right here, just on the edge here, just above the water, the angle between horizontal and the surface of the water should be just about zero. If I go and stand on the top of this hill, for example, there is going to be a slight difference in angle between my horizontal and the surface of the water. So that represents this angle here. If I assume that the Earth is flat, for example, this would be a 90-degree angle. This would not be a 90-degree angle if the Earth was round, but let's just look at this as if the Earth was flat and that this was 90 degrees. So if I'm looking in this direction to the top of the hill, and if I can accurately measure this angle here, then there's going to be a hidden angle over here. So the hill height is 206 meters. My height is 55 meters. 55 meters happens to be the height of the Ottawa River according to Google Earth. So using trigonometry, I can calculate based on the angle above my horizontal that I should see. And I should see, in this case, 136 meters. I calculated the height that should be visible by multiplying the distance in meters to that point by the angle above my horizontal, and I got 136.48 meters. How much of that hill was invisible? I subtracted my height from the hill height, and I subtracted from that the amount that was visible. That should have given me this height here. I then calculated the angle down from my horizontal, which should have taken me to the base, keeping in mind that the base, in quotes in this case, is at my height. That gave me an angle of 0.06113 degrees. If I assumed that the Earth was flat, then if I were to stand on that hill looking back at my location, this is what I would expect. I then subtracted this value from this value, and I got an angle delta of 0.068 degrees, which happened to be fairly close to the invisible angle. And in this case, I just subtracted this value from this value, and I got 0.000264 degrees. I then tried a few other samples, and in every case, I got to within 3 or 4 decimal places accuracy. So I was reasonably confident that this would allow me to estimate the angle back to my location from the other location. I went back a second time. The second time I took my P1000, taking a bunch of pictures, and I even went so far as to make a panorama by stitching these pictures back together. You can see where they were joined, with the intent of knowing that if I knew how many pixels per degree there were for that setting, then I could estimate a higher precision of the angle up to the top of this mountain range. Unfortunately, I tried using a measuring tape with different zoom levels and trying to approximate it that way. And I even made a graph here so that at different zoom levels, I could then be able to say that if it was zoomed at 30 millimeters, for example, I should expect to see that number of degrees per pixel. Unfortunately, that didn't quite work out too well, and I thought about the issue, and I went back to the Nepean Sailing Club a third time. I made sure that my theodolite was reasonably calibrated. I don't really have a way of holding the camera. I had it sitting on top of my tripod, and I was still shaking the camera enough. It didn't get as precise as I wanted it to be. But the third trip brought something out that was very interesting. And here I'm looking a little bit northwest. So I'm looking off in this direction over here, and the river flows like this. And while I was able to get the theodolite calibrated in this direction fairly close to level, I tried over here. I did get this one at 0, and as you can see, it was pointing up above the tree line over here. I tried it again. This time I tried to get this one more level as well, and I also tried to get this one lined up with the water level. And as you can see, looking downstream, it's not pointing at horizontal here. And here I'm only about maybe a meter above the water. I tried another attempt, and as you can see, the theodolite is still indicating that the surface of the water would be below horizontal over here. And then of course you've got this one over here, which is fairly close to where it should be. While I was there, this was my thinking. The theodolite app only has a resolution of tenths of a degree, and if I could interpolate a higher accuracy, I should be able to get a reasonably better approximation of the Earth's radius. So I took one pointing a little bit further up in the air, and then I took another one pointing down, and the idea would be if I could measure this distance, knowing that 657 pixels is 12.8 degrees, and I took this measurement knowing that 1108 pixels is 19 degrees, I could work out how many pixels per degree that setting should be, the total pixels by the total degrees, to get 55.15 pixels per degree. And in this case, if I measured 77 pixels, I should expect there to be an angle of 1.323 degrees. I worked out this tab over here. This would be the total pixels that I've measured along with the total degrees. My height would be the height above sea level. And let's say I go back to this point and I said, okay, this measurement over here was 402 pixels, for example, and I knew what the pixels per degree ratio was. The idea would be that I would put this value over here. It would calculate the angle above my horizontal. I would know what the lower point angle would be. This would calculate the reverse angle. I should expect to know the distance to that point and the height of that hill. These are the calculations that this triangle calculator took here to measure these angles. And in this case, I assumed the Earth's radius of 6371, and I calculated what these angles should be, including calculating the angle difference between what it should have been and what I calculated the angle to have been. And let's say, for example, in this case, I had measured 72.121 pixels and got these values here. I took these three values and I applied them in this triangle calculator this way. So in this case, I'm looking up to this mountain peak. I know what the distance is, and this is the mountain peak angle looking back to me. This is how it would have calculated the Earth's radius. Then this cell would be the expected globe Earth radius. So I had come up with that spreadsheet, looked at my photos and all of that stuff, and it was really on the third trip taking pictures of the Gatineau Hills when I noticed that the angle of the river was not anywhere close to horizontal. And so I really couldn't count on it as being a way to measure the Earth's radius. Unfortunately, I'm not able to do that where I am. And I was just about to give up and try something else when I thought of another way of approaching this problem, which allowed me to make this video. I found a website hosted by the Government of Canada that allows you to put in a geocoordinate bounding box and how you want the data represented, and they will give you the elevation data at so many steps between each point. And so I was able to get the elevation data for this square over here that included these hills. So I added functionality to my app that I was working on that would let me generate what the skyline should appear like if the Earth was a globe or if the Earth was flat. And so the way I did this, I locate myself somewhere geographically. I have an azimuth and I have a horizontal field of view degree angle like this. And I know that this is so many pixels wide. I know the angle that I want, so I can calculate the azimuth in each of these directions. So I'll start at this point and I'll go off in this direction, calculating the globe Earth or the flat Earth elevation angle for each point at each step along the way. And then once I've got the highest angle up to the peak, then I can draw a line back to my horizontal. So the only difference between the globe mode and the flat Earth mode is how the horizon line is computed. And as you can see, if I expected the Earth to be flat, I really would not see much of a deviation where the ground meets the sky. Whereas on a globe Earth, you can see that the ground looks fairly low here, and then there's a hill. There's another hill over here. Then it steps down like this, and then it steps down a bit more over here. And sure enough, the ground is fairly low over here, and then it steps up a bit more over here. There's a few little ridges along the way here, and then it starts to step back down a couple of levels, and then it is relatively flat over here again. Using real data, calculating for the globe, the skyline matches my location. It does not match my location if the Earth is flat, but I didn't want to just stop there. I wanted this to be another viable way of calculating the Earth's radius. So all of this hinges on how well you can calculate this angle above your horizontal reference line. And since I'm calculating this to generate a pixel, I'm able to use the original value before I turn it into an integer. And I can, of course, zoom in and get a much better mountain range with a much higher length of pixels. Unfortunately, right now I can't see these sample readings, so I'm going to tame it down a bit, and I'm going to come back over to here. So at this zoom level, 810 pixels represents 7.0875 degrees. My height happens to be 58 meters above mean sea level. And if I pick one of these, let's say I was able to measure 101.386123 pixels above horizontal, and the distance to that point was 18.11199,602, and the height of that hill happened to be 364.1600646 meters. These measured readings would produce these three calculated values, and if I fed them into a triangle calculator like this, I would expect the Earth's radius to be 6,380.154 kilometers. I can try another one. Let's try this one, 6,380.058 kilometers. Let's say my camera isn't zoomed in at this level. Let's say it's zoomed in at this level, and I'm not at 58 meters above. I'm at 54 meters. So my height is 54 meters, and I've worked out the angle if I pick this one, or if I had a reasonably decent theodolite and I was directly able to measure this angle here, I wouldn't need any of this. I would just be able to grab this directly and compute this value directly from this value. I'm still well within the ballpark. So theoretically, this should be a fairly good way to estimate and approximate the Earth's radius. I'm going to leave the link to this spreadsheet in the description below. If you made it this far, thank you for watching. If you like this video, I would appreciate the subscribe if you're not already. That's going to be it for the moment. Thank you for watching, and I'm going to see you in another video soon enough. So bye for now.